Welcome to Chapter 21. This is the second of the two chapters on electrostatics, and I do think they're both rather challenging. Chapter 21, challenging for different reasons, I think, than Chapter 20. Mainly that the topic, the electric potential, is a complex topic, and it can easily be confused with other things. If we think back to Chapter 20, we know that the electric field is the agent that causes electric force on charges. But electric potential can be thought of as a potential energy per charge. So the units for electric potential are joules per coulomb, energy per charge, but volts is the term we usually refer to that as. So a volt is the same as a joule per coulomb. So when you think about the potential difference between the two plugs in your outlet, in your wall outlet, we say 120 volts. That's not saying how much energy is flowing, but for every coulomb of energy that flows, we would end up having 120 joules of potential energy being converted into something else, like heat, light, motion, if you're moving a fan or something like that. So there's a reason we a lot of times are interested in the electric potential or potential difference between two locations. So table 21.1 in your textbook, and I'm going to check that just to make sure, has got some examples. And so the brain activity, batteries, things like that. Your car battery, interestingly enough, is not 12 volts like a lot of people think it is. It's actually about 14. It needs to deliver 12 volts of electric potential at a minimum. And so since batteries have internal resistance, that's why the car batteries tend to be about 14. So when there's potential difference, it'll take work to cause positive charge to move from an area of low potential to an area of high potential. In other words, we think of areas with lots of positive charge as having high potential energy because it would take work to move a small positive test charge to that location. So we think of an area of high potential as being nearer to positive charges. It's a metaphor, really, but it's a good way of thinking about things. So we measure electric potential with a voltmeter, and we're going to end up using voltmeters in the course when we think about electric circuits and things like that. So combining the idea of electric potential with potential and kinetic energies can be super helpful. A big idea is that when we get an object, if it's speeding up, it's going to gain kinetic energy, and therefore it has to lose potential energy. So I really like to think about it like that. So think about whether a charged object is speeding up or slowing down. Then you can tell whether or not it's gaining or losing kinetic energy, and from that you can think about whether it would be going to a higher or lower potential. Now it's a little more complicated if you have negative charges. Okay, so we normally think of energy as being joules, and this is the next section, by the way. If 1 coulomb of charge passes through one potential difference of 1 volt, that charge will gain or lose 1 joule of electric potential energy. But an electron volt is another measure of energy, and it's much, much, much smaller. So in fact, since one fundamental charge on a proton or electron is 1.6 times 10 to the negative 19th joules, 1 electron volt is 1.6 times 10 to the negative 19th joules of energy. So it's the energy an electron would gain or lose passing through a potential difference of 1 volt. In section 21.4, and 21.3, by the way, talks a lot about conservation of energy. So sort of like I was saying earlier about thinking about whether something's gaining or losing kinetic energy. So section 21.4 starts off with this relationship, which is that voltage is energy again per charge. If I look at this potential energy per charge, joules per coulomb, that agrees with what we've said so far. Now inside a capacitor or a parallel plate capacitor, the electric field can be thought of as change in electric potential over distance, or volts per meter. So far in Chapter 20, we've really looked at electric field as being newtons per coulomb. Well, I'll go through a little bit of a proof where we see that a Newton per Coulomb is exactly the same thing as a volt per meter, which is kind of interesting. So electric field strength is actually equal to the potential difference divided by distance. Rearranging this formula gives us this formula. So there's a way that I mentioned that. So essentially we've got energy or electric field here, newtons per coulomb or volts per meter. If we look at these, if we cross multiply this, we get force times distance equals voltage times charge. Well, what is a force? A newton. What's distance? A meter. Newton times a meter is actually a joule. What about over here? A volt is essentially a joule per coulomb. Charge is in coulombs, so we end up with joules. So basically we're saying that energy is equal to energy. So that's why both of these two relationships for electric field actually really mean the same thing. So I'm going to go through and do an analogy here, and we'll probably do this in class as well. So again, if you want to skip over this, we can come back to it. But there's a lot of analogies between electricity and gravitation, and I think they're helpful for understanding things. So if you think about it, we can have uniform gravitation fields, which is close to the surface of the Earth. That's just a ratio of weight, which is a gravitational force, divided by mass. So near the Earth, we have 9.8 newtons for every 1 kilogram. We also think of electric fields as a ratio between force and charge. So here we would find out the force on an object by multiplying its mass times the gravitational field strength. And we get kilograms times newtons per kilogram. Here, to find the electric force on an object, we'd take the electrical field strength and multiply it by the net charge on the object. So basically newtons per coulomb multiplied by newton or by coulombs gives us newtons. This is how we figure out forces between 2-point sources for mass. This is how we figure out the electric force between 2-point charges for electricity. Gravitational potential energy can be thought of this in a uniform field. mg, which is basically the gravitational force, times change in elevation, or h. Here, we could think of electrical potential energy as being charge times voltage potential difference, which is energy per charge. So really what we've got here, this G delta H is kind of like the delta V here, whereas this charge is equivalent to the mass. Now, when we have a non-uniform case, so a place when we're looking at gravitational potential energy, say not close to the surface of the Earth, this is the formula for it. And it's on your formula sheet in mechanics. I believe it is M29. There we go. But we didn't really use it much in first year physics. The negative basically says that the gravitational potential energy between two objects, like a planet and a moon or a planet and a satellite, is negative if that second object is in a stable orbit. Here, the gravitational potential energy looks very similar. K Q1 times Q2 over R. Here we can have gravitational potential energy that's negative when one of these charges is opposite the sign of the other charge. We have positive potential energy when they have the same charge. Well, what's the similarity? Here, two masses are always attractive, so when you have objects that are attracting each other, they'll have a negative potential energy. Here, when the charges are opposite sign, they'll attract each other, and again, they'll have negative potential energy. When the two objects have the same amount of the same sign of the charge, they'll repel each other. We think of that as positive potential energy. So unfortunately, when you hear the word voltage, there's a lot of different ways to think about that in terms of the terminology. So it's called potential or potential difference or electrical potential or voltage difference or delta V. These really mean the same thing or very similar. People unfortunately use them a lot interchangeably. So this is what I talked about earlier. If finding the potential and potential energy using point charges. So we think of this as a fixed charge or a source charge, and this is a test charge. We're going to say that at infinity, these aren't interacting. So we would think about the fact that if this is an infinite distance away from this charge, there would be zero electric potential, and there would be zero potential energy. So there's no force acting on this charge or this charge. Here, we have a positive and a negative, and again, they're an infinite distance away. Again, there's no interaction, so there's no potential energy, and there's no electric potential at infinity from this charge either. Near the positive charge here, in other words, if we move this thing close to this fixed charge, it's an area of high potential, so we would have a high voltage. We would think about calculating that with this formula here, which I think will be brought up again in a little bit anyhow. We would also think as we bring this thing closer to the positive, we're going to gain potential energy. So for a positive charge to get close to another positive charge, essentially it either has to have kinetic energy, or you would have to push or do work on this test charge to get it close to this. Over here, the potential is still positive as this thing gets close to this positive charge. Why? Because electric potential in space is dependent on the fixed charge. In other words, this is causing positive potential everywhere around it, whether or not this small test charge is positive or negative. Here, the potential energy, however, is negative. So the potential is positive because the Q is positive, but the potential energy is negative. So that probably seems odd, but the way to think about it is here, for this negative to get close, if we had this negative further away, all we'd have to do is release it, and it would accelerate over to the left toward this fixed charge. So if it's speeding up, it's going to lose kinetic energy, or pardon me, lose potential energy because it's gaining kinetic energy. So as the negative charge would zoom over here to the left side again, it's going to gain kinetic energy, therefore it has to lose potential energy. And since we define potential energy at infinity as being zero, that means that as this test charge gets close to this fixed charge, we're definitely going to have negative potential energy. Whereas over here, if we want this test charge to get close to this positive, again, either it would have had to have positive kinetic energy at first, or we would have to push it, which would be doing positive work on the system. So if the test charge doubled in magnitude here, that's this one, the potential at this particular location doesn't change. Why? Because the potential at a location in space depends on the other charge, or in this case, the fixed charge. If we doubled the fixed charge here, the electric potential at this point in space would in fact double with this rule down here. And that's what's talking about. Here, if the test charge doubles in magnitude, again, the electric potential at this location doesn't change because at this location it's caused by this charge. If the test charge doubles in magnitude, the potential energy would double in magnitude, but notice that's getting twice as negative, since here the interaction between this causes a negative potential energy because it would really want to accelerate going toward that location. And we define zero potential energy as being at infinity. So that's kind of a lot going on. I've got a couple other pages here, 3 other pages, and then some examples. So I'm going to try to get through these 3 pages to some extent. Actually, I don't think I'm going to do this. This is one I'd look at. We will do this in class at some point. I think it'll be more helpful to do it as a class. But if you remember this sort of orange sheet of paper, this is where this is. And I would go back and look at it. 21.7 and 21.8. deal with capacitance and capacitors, which were also talked about a little bit in chapter 20. So capacitor is basically a way to separate charges, and specifically it's on two conductors with equal and opposite charges. So in chapter 20 we learned this was true within a capacitor. Now we're going to see that capacitance is a ratio of an object's charge to voltage, which is interesting. So the units for capacitance are in farads, that's coulombs per volt. So it basically is how many coulombs of charge can you hold at a certain voltage. And again, this is the standard unit. So as the voltage across a capacitor increases, so does the charge that it can hold. Hopefully that makes sense. So when we think about a charge versus voltage graph, the slope of this graph would tell us, again, basically the capacitance. And if we look at the charge and voltage graph, if we look at the area of the graph, that tells us the energy that's stored. So if C equals Q over V, then Q equals C times V, which is like this. So if this is a triangle, you could say 1/2 CV squared is equal to the energy stored in a capacitor. So either of these two would work, and they actually mean the same thing. If you can combine the result for a uniform electric field, so that's this, again, could also be force over charge, but we're going to look at this. An electric field within a capacitor, that's this. So we basically set the right side of this equation equal to the right side of this equation. And we rearrange that. We get that Q over delta V is equal to EOA over D. So essentially, since Q over V is capacitance, it says capacitance is equal to this constant times the area divided by the distance between the two capacitor plates. So, in other words, it basically is looking at how much charge can you hold, right, and how far apart those plates are. So the more area you've got, the higher the capacitance. The smaller the distance between the plates, the higher the capacitance, which is actually pretty interesting. A dielectric is actually something that can happen to a capacitor. And most practical capacitors, such as the ones in your cell phones, have dielectrics in them because it maximizes the capacitance while minimizing the space. It's an insulator, pardon me, that was a drink, between the conducting plates. And when a capacitor is charged, the insulator becomes polarized with kind of an internal electric field pointing opposite that of the field caused by the capacitor. So if this is a capacitor, we've got, say, 6 volts here for a battery. We have 6 volt potential difference here. And notice the arrows being about the same distance apart show a uniform electric field. Well, if we have a dielectric sandwich, essentially what we get is that the particles in here can't move, so it's not a conductor. So, for example, foil or copper or something like that would not be a dielectric. Air is a dielectric, dry wood would be a dielectric, plastic or rubber would be a dielectric. At any rate, inside there, the molecules rearrange themselves so that they are polarized opposite the positive and negative charges on the capacitor plates. So essentially what's happening is, if these molecules polarize, you get kind of a bunch of these negatives up close to these positives. For the same 6 volt push, that means we can pile on more positives on this top plate and more negatives on the bottom plate. Why? Well, although they're certainly repelled by each other still, and these are still repelled by each other, they're also somewhat attracted to this dielectric, to the negatives up at the tippy top of the plate. And down here, somewhat attracted to the negatives. So you get, like I say, kind of a back electric field. That means for the same 6 volts, if you're hooked up to this battery the whole time, you can store much more charge. So therefore the capacitance goes up. So overall, when you look at the formula for capacitance, one of them is this. Well, if you have a dielectric, it's multiplied by this capacitance value. So essentially, if this now holds triple the charge at the same 6 volts as it did over here, our dielectric constant would be 3. And this capacitance, therefore, would be 3 times higher. And that's what I'm going to quit for right now. I'm going to upload, and we'll do the sample problems.